Welcome to the Nostromo, home of physics principles. So by the end of this video lesson, you should be able to understand that all physical quantities consist of a numerical magnitude and a unit. You should be able to make reasonable estimates of physical quantities included within the syllabus. You should be able to recall the following SI base quantities and their units, that is mass, measured in kilograms, length, in meters, time, in seconds, current, amperes, temperature, Kelvin, and the amount of substance, which is measured in moles. You should also be able to express derived units as products and quotients of the SI base units and use the named units listed in this syllabus as appropriate. You should be able to use SI base units to check the homogeneity of physical equations. You should be able to use the following prefixes and their symbols to indicate decimal multiples or multiples of both base and derived units, that is the pico, nano, micro, milli, centi, deci, kilo, mega, giga, and tera. You should be able to distinguish between scalar and vector quantities and give examples of each. You should be able to add and subtract coplanar vectors. And finally, you should be able to represent a vector as two perpendicular components. Let's start the lesson by looking at the term physical quantity. What is a physical quantity? The term physical quantity is used to represent measurable features of an item. So the equation which is used to define physical quantity is physical quantity is equal to number plus unit. For example, let's consider the mass of this book. The mass of the book is equal to 500 grams. It is that property of the book that you can use a measuring instrument to find its magnitude. Book is the item. 500 grams is the magnitude of the physical quantity. It is very important that the magnitude of a physical quantity be expressed using a number and a unit. Other examples of physical quantities include area of a playing field, speed of a car, volume of water in a container, and so forth. In quoting any measurement of a physical quantity, two items need to be stated. The first is the numerical value of the quantity, and the second is its unit. It is important at all times to think and write the value and the unit of any quantity together. Apart from the technical accuracy of writing in this way, it will also help you to acquire a mental appreciation of the size of the quantity you are considering. For instance, if the diameter of a wire is found to be 1.46 millimeters, this appears reasonable. If the diameter is found to be 1.46 meters, then something is wrong. A value stated as simply 1.46 does not give this check and is therefore meaningless. Realizing whether a particular value is possible or not is something which comes with experience, but it is only by thinking about the size of the physical quantities that this experience can be gained. There are two types of physical quantities. The first type is referred to as basic physical quantities, and the second type is referred to as derived physical quantities. Now, what is a basic physical quantity? A basic physical quantity is one which cannot be obtained from any other physical quantity. There are 7 basic physical quantities. Each basic physical quantity has an SI base unit. There are therefore 7 SI base units. And this can be put in a table as follows. So in this column, we have basic physical quantity, then we have its SI base unit, and then we have the abbreviation for the SI base unit. The first one is length, its SI base unit is meter, and the abbreviation for meter is lowercase m. Time has the SI base unit second, and the abbreviation for the SI base unit for time is S. The third basic physical quantity is mass, measured in kilograms, and the abbreviation for the SI base unit is kg. Electric current is the fourth basic physical quantity. It has an SI base unit referred to as ampere, and the abbreviation for ampere is uppercase A. The fifth is thermodynamic temperature, measured in Kelvin, and the abbreviation for Kelvin is K, uppercase K. Amount of substance is the sixth basic physical quantity. Its SI base unit is mole, and the abbreviation for the SI base unit mole is MOL without the E. The last basic physical quantity is luminous intensity, measured in candela, and the abbreviation for the SI base unit is CD. But in this syllabus, we won't deal with this seventh basic physical quantity. We will deal with the first six. Now let's look at examples of basic physical quantities. We are going to look at an example of an examination question, and this is in October-November 2013, paper 1, question number 1. This question states as follows. Which row shows an SI base quantity with its correct unit? If we go back to the table, we find that charge is not an SI base quantity. So this rules out A. Current, however, is an SI base quantity and its unit is ampere. However, let's check C before we settle for B. Potential difference is not an SI base unit, so that rules out C. D, temperature, thermodynamic temperature is an SI base quantity, but its unit is not degree Celsius. So we settle for B. Now let's consider derived physical quantities. What is a derived physical quantity? A derived physical quantity is one which is obtained from other physical quantities by either multiplication or division of those other physical quantities. Derived physical quantities are therefore defined. To derive a physical quantity is to define it. When we define a physical quantity, we show how it is related to other physical quantities which are familiar to us. An example is pressure. Pressure is defined as force exerted normally on unit area. The equation which is associated with this definition is pressure is equal to force over area. This is the equation which is associated with the definition of pressure. It is important to learn how a physical quantity is defined as well as the equation which is associated with that definition. So each time you define a new physical quantity, be careful to recall its definition as well as learning the equation associated with that definition. In addition, you should state its unit. If the unit has a name, you can go ahead and define that unit. For instance, the SI base unit of pressure is Pascal. The Pascal is defined as the pressure exerted when a force of 1 Newton is exerted normally on an area of 1 square meter. So 1 Pascal is equal to 1 Newton over 1 meter squared. So we can see that this unit, the Pascal, is defined in terms of other units. This one is very important. Now, we'd like to note a few points about derived physical quantities. The first point to note is that there is only one way of defining a physical quantity. There is therefore only one equation which is associated with that definition. We must learn and recall both the definition of the physical quantity as well as the equation which is obtained directly from this definition. Point number 2. A physical quantity is defined in terms of other physical quantities, while a unit is defined in terms of other units. For instance, it is wrong to define speed as distance covered per second because while distance is a physical quantity, second is a unit. So speed should be defined correctly as distance covered per unit time. Unit time is a physical quantity. Second is a unit. While in the previous definition, speed was defined in terms of distance, which is a physical quantity, and second, which is a unit. This is clearly not acceptable. Now let's look at examples of derived physical quantities. We have already seen that pressure is a derived physical quantity. Its SI unit is Pascal or newtons per meters squared. It can be shown that its SI base unit is kilograms per meter per second squared. Force is the next derived physical quantity. Its SI unit is Newton, and the Newton has the SI base unit kilograms meter per second squared. Speed is a derived physical quantity measured in meters per second, and of course the SI base unit is simply meters per second. Power has the SI unit watts, and its SI base unit is kilograms meter squared per second cubed. To derive the SI unit of a derived physical quantity, we follow the following steps. Step number 1. Recall the equation associated with the definition of that physical quantity. Step number 2. If the quantities used to define it are themselves derived, you must further break them down until you get all the quantities used being basic physical quantities. Step number 3. Recall the SI base units of all the basic physical quantities. Let's look at an example. And this one is in October-November 2013, question 1, variant 3, number 2. In this question, we are asked, what is the unit of power expressed in SI base unit? So we have said the first step is to recall the equation which is associated with that definition. So power is equal to work done per unit time. Although time is a basic physical quantity, work is a derived physical quantity. So work is defined as force times distance, of course divided by time. Force is a derived physical quantity, and it is defined as the rate of change of momentum, which is ma, of course times d divided by t. At this point, we can see that the units of power, put it in square brackets like this, is the unit of mass, which is kilograms. The base unit of acceleration, it is meters per second squared. Base units of distance, which is the length, is meters, and time is in seconds. This gives us kilograms. This meter and this meter gives us meters squared, and this is per second cubed, like that. So kilograms, meter squared per second cubed is the SI base unit of power. And so the correct answer is A. So in order to get the answer to a question like this one, it's not mere recall. There is a process which must be followed. The next example is in October-November 2013, Paper 1, Variant 2, Question 2. And we are told, what is the unit of resistance when expressed in SI base units? Again, we proceed as follows. We must remember the definition of resistance. Resistance is the ratio of the PD to the current which is flowing. Potential difference is defined as work per unit charge. So we are going to have work divided by charge, which is Q, of course, divided by current, which is I. Work is force times distance. Of course, we can have this charge come over here, and we can multiply that by the current. Force is defined as MA. Of course, we've got the distance there. Q is I, T, and there is this other I there. This I and this one. So the unit of resistance, can put it in square brackets like this. The unit of mass is kilograms. Acceleration is meters per second squared. Distance is meters. Divide by current is ampere squared, because it is ampere times ampere, and then there is this second there. We go ahead and simplify this. Kilograms is here. Then we have meters times meters, meters squared. Then we have per second cubed. And then we have per ampere squared. Like that. So when we check the choices, kilograms, meter squared, per second cubed, per second cubed, per second squared. So the correct answer is B. Again, you can see the procedure for arriving at the answer is the same. You must recall the equation which is used to define that physical quantity. Or rather, you must recall the equation which is associated with the definition of that physical quantity. And then, if that physical quantity is expressed in terms of other derived physical quantity, you must break them down. So you must work backwards until finally you get an equation with basic physical quantities. Even acceleration is a derived physical quantity. It's easy to get the SI unit of acceleration, which is just meters per second squared. That is why I wrote it first time here. Meters per second squared. Otherwise, everything else is in terms of basic physical quantities. Now let's look at a new term referred to as homogeneity of physical equations. Base units can be used to check the homogeneity of physical equations. A physical equation is said to be homogeneous with respect to base units if the base units on one side of the equal sign is the same as those on the other side. In other words, base units can be used to check the correctness of a physical equation. Let's consider an example in an examination. And we are going to look at paper 1 of the year 2002, number 3. Now, in this question, we are asked, which formula could be correct for the speed v of ocean waves in terms of the density rho of seawater, the acceleration of free fall g, the depth h of the ocean, and the wavelength lambda? Now, this is how we go about this question. We must know the SI base units on one side of the equal sign. For example, the base IS unit of velocity is meters per second. So we start by writing those. Meters per second is equal to, is a square root sign here. G, which is acceleration due to gravity, has got the units of acceleration, which is meters per second squared. And lambda, which is a length, has got the units meters. Meters times meters is meters squared. And then we've got per second squared. And then there is this square root. We realize that this is like meters squared divided by second squared and then square root. We further break this one down as meters squared, square root of meters squared, divided by the square root of seconds squared. And obviously this one is like meters divided by seconds, which is meters per second. So we find that in this choice, the unit on the left-hand side of the equal sign is meters per second, and the base unit on the right-hand side of the same equation is meters per second. So this equation here is homogeneous with respect to base units. We can go ahead and use the same method for B. But when we do that for B, we'll find that the unit on the left is not equal to the unit on the right. Let's see what happens here. The unit on the left is meters per second. The unit on the right is square root of G. G is meters per second squared. H, which is depth, has got the units meters. These meters and these meters are going to cancel out. And then you are going to have the square root of per second squared. And the unit on the right hand side is per second. So we observe here, on the left hand side we've got the base units meters per second. On the right hand side we've got per second. Obviously these units are not equal to these units. Therefore this equation is not homogeneous as far as base units are concerned. Let's consider the next subtopic, and this is scalars and vectors. Now, what is a scalar and what is a vector? We will start by defining a scalar. A scalar is a physical quantity which has magnitude only. Examples of scalars include distance, speed, energy, work, time, power, mass, and so on. Each time you define a physical quantity, it is important to state whether it is a scalar or a vector. How about vectors? A vector has both magnitude and direction. Examples include displacement, velocity, force, acceleration, momentum, electric field strength, and so on. Let's now consider a question in an exam. And we look at May-June paper 2013, paper 1, question number 1. Which pair of quantities contains one vector and one scalar quantity? Displacement is a vector, force is a vector, so both are vectors. Kinetic energy, so A is wrong. Kinetic energy is a scalar, power is a scalar, so both are scalars. Acceleration is a vector, momentum is a vector, both are vectors. While velocity is a vector, distance is a scalar, so the correct choice is D. Now let's consider components of a vector. The effect of a vector in a given direction is referred to as its component in that direction. A vector can have an effect in any direction other than in a direction which is perpendicular to its own line of action. That is, the component of a vector in a direction which is perpendicular to its own line of action is 0. In other words, if we have a vector acting in this direction, maybe a force acting in that direction, its component in a direction which is perpendicular to its own line of action should be 0. If this is the force, we want to find its effect in a direction which is perpendicular to its own line of action. We want to split this force. We want to resolve this force in this direction. Its component will be 0. That is what we mean when we say that the component of a vector in a direction which is perpendicular to its own line of action is 0. When we find the effect of a given vector in a given direction, we say that we have resolved the vector in that direction. It is common practice in mechanics to resolve a given vector in two directions which are perpendicular to each other. Now let's consider an examination question. And this is in the year 2013, question paper 1, variant 3, number 1. In this question, we are told that the diagram shows a displacement vector, 5.0 kilometers, in this direction. What is the vertical component of this displacement vector? In this question, therefore, we proceed as follows. We have to resolve that vector in this direction. Its component in this direction is 5 cos 53 degrees. But what we require is the vertical component, and that is 5 sine 53 degrees, and this gives us 3.99 kilometers. This is of course approximately 4.0 kilometers, and so the correct answer is B. Now let's consider adding vectors to get the resultant vector. Resultant vector is the sum of two or more vectors. The steps followed when we want to get the resultant vector are as follows. Step number 1, we connect the vectors head to tail. Step number 2, join the first tail to the last head with a straight arrow pointing from the first tail to the last head. This arrow represents the resultant vector in both magnitude and direction. Let's consider an example, and it is in October-November paper 2013. In this example, we are told that vectors P and Q are drawn to scale. Which diagram represents the vector P plus Q? So the first step is that we are going to join the tail of this vector to the head of this vector. So this is the vector. So we are going to slide it from this position all the way so that its tail comes here, like that. Then we draw a line from the first tail to the last head. And this is the resultant vector which represents P plus Q. And the best option given here is option A. So A is the correct answer. Now let's look at subtracting vectors again to get the resultant vector. In this example, we are asked which diagram represents the vector P minus Q. We are given P and Q. The first thing we realize is that if we are given Q and we are required to get minus Q, we just need to get a vector whose length is the same as this, but it points right in the opposite direction. Or we just need to rotate this vector so that it points in this direction. So this vector is minus Q. Again, we follow the same method. We are going to join the tail of this vector to the head of this vector by sliding it all the way up to that point. And the resultant will be from the first tail to the last head, like that. And the answer again is C. So let's stop this lesson at this point, and in our next lesson we look at the second topic, which is measurement techniques. techniques. You can also join my Google Classroom for more information, video tutorials, notes, and targeted assignments. Just send me your email and I'll send you the link. You can also subscribe to this channel for more tutorials.